I'd like to thank the organizers for the invitation. It's my first time in Taiwan. So I'm going to give a talk on some topics in mean curvature flow, and I was told that you've all seen at least some of this material, but I want to maybe focus on certain aspects of it, specifically kind of the variational theory of mean curvature flow, and specifically how that relates to studies of singularity formation and their properties. But let me just start with maybe this first lecture, the first two, to just sort of set up basic stuff and set up notation. Right. Right. So again, we're looking at this mean curvature flow. Okay, and so this is like a kind of very natural geometric flow of submanifolds, and I'm going to focus on the case that's sort of where it's most well understood, which is when the sort of the flow of hypersurfaces in Euclidean space. Right, so in general, the submanifolds could have arbitrary codimension, and the ambient space could be any Riemannian manifold, but I'm going to focus on the case where we have the Euclidean metric and a codimension 1. Right, and so just to define what I mean, so we're going to look at is a hypersurface. So this is the basic object we're flowing, and what I mean by hypersurface is that it's a proper connected smooth codimension. Okay, and I'm going to be interested in both the case where my hypersurface is closed and where it's non-closed. So let me just give some examples. I'm being pedantic here, but I think sometimes these are useful in understanding things. So the prototypical example would be a unit sphere. Or the flat plane. Right, so this one, of course, is closed, means it's compact and without boundary. This one is just proper and not necessarily closed. But I think what's more illustrative is sort of the non-examples. So these are things that are not considered hypersurfaces by me. So first of all, anything with a self-intersection like this. So this is not, here it's not locally a submanifold. So of course you could think of this in two different ways. Either you could try and think of this as an immersed manifold, so it's still smooth, it just has self-intersection. Or if you take the perspective I prefer, which is a more, say, geometric measure theory perspective, this would be a singular point. So we'll maybe discuss that later in the series. Another one is, it's worth mentioning, is of course, something like this is like an open disk is not a hypersurface because, of course, it's not proper. So if you take its closure, you gain a boundary, which is not so this is non-proper. And there's, of course, weirder and more exotic things that are ruled out. So, for example, something where it's like, this would be an example where maybe it's complete, but it's not proper. And the idea is that it concentrates after going back and forth an infinite number of times at some line. So this is also non-proper. Okay, so this the problem here is that there's locally the sort of volume becomes infinite at some points, which we don't want. And of course also something like a manifold with boundary. Okay. Okay, and then just to be, it's also convenient. Shadow is annoying. So sometimes I'm going to consider like an open domain, and then I'll think of a so here, if I just mean it's a hypersurface, is of course it's just a proper embedded, connected, smooth codimension one submanifold of this domain. So this, of course, allows me to sort of allow boundary if I have an open domain. So, for example, if my domain omega is the ball, so if I have the open unit ball, then I can sort of think of something where the boundary, in some sense, lies in the boundary of the ball. So that would be considered a submanifold or a hypersurface in my notation. Okay. Yeah, and then another remark. Right, so I'll sometimes want to distinguish, or sometimes helpful to distinguish between a point P in say a hypersurface and its position vector x of P, which we think of as sort of a vector in the ambient space. Okay, so they're sigma is a subset of Rn plus 1, but we want to distinguish between its points and its position vector. Comes up in notation frequently. Okay, and then one final kind of thing, which goes back to this definition of hypersurface, is one of the nice things about, from my perspective, about these submanifold problems is that especially the codimension 1 ones, so if you're a hypersurface, that kind of implies that you're locally graphical. In other words, basically at each point in the hypersurface, you can locally write the surface as a graph over the tangent space at that point. And this of course gives natural coordinates. So this gives and this is very useful from the point of view of analysis, because you have to you see very easily how to control, say, the coefficients in say your elliptic or parabolic operator, which of course is always trouble in these geometric problems. And let me just remark a very useful lemma that one often uses in this. So if sigma, say 4s, and something you can control the curvature. So so here, this is the second fundamental form of the surface. If this is bounded by 1, then for any point P inside of say sigma intersect the ball of radius 2s, 0. The set sigma ps, which is the component of this set can be written as a graph of a function u defined on tangent space of sigma, and we have the following bounds, which is that the gradient of u. Okay, so the idea is if we have a point P on our surface, then if we can control the second fundamental form, then we can actually get the sort of the inverse of the curvature gives us a radius where we can write the surface as a graph with good good estimates. And that the point is, we'll see maybe when we get into some of the theory, this will definitely kind of simplify our analysis. One of the points, though, is that of course we don't necessarily know how many components of the surface kind of come in to this ball. So we're not saying anything about those other ones. We're just saying about this specific component through P. Okay. All right. So that's just a background, and I just wanted to mention it. Okay, so as I said, we're interested in the mean curvature flow, which of course is going to arise very naturally as a kind of negative gradient flow of the volume functional on hypersurfaces. So before I get to that, I just want to mention another important sort of formula, which is the so-called first variation formula. And this is something we're going to use again and again in these first lectures, the first variation. Okay, and this tells us essentially that the mean curvature arises naturally from a variational point of view when you describe how volume changes under deformations of a hypersurface. So the idea is, let's again fix a hypersurface. And let's fix say a C1 vector field, Z. Let's say, a vector field with compact support. And if we let phi sub t take be the time t flow, then the idea is we can consider the variation phi t sigma. This is a family of deformations. And so the idea is we have a sigma, which is sigma naught, and then whatever the vector field tells us to do is, this is maybe sigma t, and we get this family like so. And what the first variation formula tells us is how the infinitesimal change of the volume of this family. So okay, so we have the following formula, which says that the change at t equals 0 of, this is the right. This is the first variation formula. This is given by the integral over sigma of the so-called divergence of sigma of this vector field Z. But here, the divergence of sigma of a Z. Notice Z is not necessarily tangent to sigma, so this is just by definition the sum right here the so at P. Okay, so this is the first variation formula, and the point about this formula, which maybe we'll come to later, is of course here everything I said is smooth, but of course as long as this vector field is C1, this formula is going to make sense with much lower regularity in sigma. So for example, if sigma is a Gokuli-Lipschitz or even weaker notion, this formula makes sense. So we can get a notion of weak mean curvature, because the point is, if you use this formula, and you break z into its tangential and sort of normal part, you see that this has the formula right, this is the tangential part of c. And then it has a minus sign, and there's this vector field H, which is normal to sigma, dotted with z. So this is normal. And since this is a divergence of a compactly supported vector field, which is tangent to the surface, the divergence theorem tells us that this part is irrelevant, and we have the okay. So here and here, of course, H sigma is the so-called mean curvature vector. And the point is, right, if say sigma is two-sided, which it will always be in the case we're considering, but suppose, let's suppose when sigma is two-sided with, say, unit normal n sigma, then of course this mean curvature vector is minus the scalar mean curvature times n sigma. Okay, and it's an easy computation. Just a remark: this mean curvature one can check is actually computed as the Laplacian of the position vector. Okay. Okay, so this is this mean curvature vector, and this is the first variation formula. And the reason I mention it this way is, of course, this all is going to make sense in lower regularity, which means that we can do a lot of interesting weak formulations of some of the things that I'll mention today and tomorrow. Okay, and just as an example to be clear, right? If you look at the RSN, which is the sphere of radius n. Radius r, then we have that the mean curvature of sigma is minus n over r squared times the position vector. Okay. So, in other words, okay. And again, the point is here the mean curvature is the sum of the principal curvatures, not the average. Okay, and that's my convention. Okay, so that's all the setup. So let's get to the punchline. So what is the mean curvature flow? Okay, so the mean curvature flow is going to be, formally at least, sort of we want it to be the negative gradient flow of area, or volume. Right, and so what that means is we want to move it, in the direction that sort of decreases the area most rapidly. And so what the first variation formula tells us that implies is that in order to make a negative gradient flow of area, it makes sense to move the surface in the direction of the mean curvature vector. So this implies that we want to to do this, we should flow a surface, a hypersurface, in the direction of its mean curvature vector. right? And in other words, more precisely, if we have, say, a family, sigma t, this is some interval, as I say, a family of hypersurfaces, is a mean curvature flow. Precisely when we look at how the, say, the position vector is evolving precisely by the mean curvature vector of t. Okay. And the point is, as I mentioned, because this is somehow the Laplacian of the position vector, it looks exactly like a heat equation, except for the metric where we're taking the Laplacian with is dependent on the surface. So this is really a nonlinear heat equation. Okay. And again, just to illustrate roughly what we would expect to happen is if we had some kind of peanut shape, then the mean curvature here is pointing in. This is the mean curvature vector. And points out here, and it's sort of 0 at some inflection point. So if we sort of evolve this by this, we would expect this part to shrink in and this part to push out, and so it would become sort of, smaller and less peanut looking. So this would be the what this flow would do. So let me make a remark. I mean, this is formally what's happening with the equation. A little more precisely, so suppose we had some smooth map F that took some abstract n-dimensional manifold across an interval 2Rn plus, and with each basically what this equation here, this mean curvature flow equation, really should be understood to mean is that there's a smooth map from a manifold across I, where at each time we're parameterizing one of the sigma t's, and if we take the change of the position vector at a given point p and t, then that's precisely the mean curvature of sigma t at the corresponding point p of t. Okay, so here we're thinking, instead of as, say, hypersurfaces or subsets, here we're really thinking of a map. Right, so this is an evolution of a parameterization, whereas this is an evolution of a hypersurface. And just as a remark, which I'm sure you've seen, but I just want to mention, of course, if you fix a p in this parameterizing manifold M, and you consider the map T goes to f of pt, right? This traces out a curve in space. This curve is always this sort of is. If you think about it, this is where like a point on the flow, kind of where it would evolve under the flow. This curve is always sort of orthogonal at the appropriate time to the sigma t. Right, so it's always moving in some sense normally to the hypersurface. And the point is, this is sort of if you really think about it, I mean, this is an extra assumption that's not really, strictly speaking, necessary. So this is sort of an extra hypothesis. If you're thinking about it in terms of purely in terms of maps instead of sets. And so if you want to remove this, you can remove this and then consider a more general form of this equation where you look at the normal part of the change of f. Okay. So this is sort of basically, if you have a map F that satisfies this, then up to reparameterization, it satisfies this. But the point is, the idea is this is a geometric equation, so there's this huge diffeomorphism invariance when you think of it in terms of parameterization. So, this also comes up in Ricci flow. The nice thing about mean curvature flow is everything is much simpler in terms of this sort of gauge fiction. So actually to go from this to this is sort of an ODE problem and doesn't require all this extra work you need to do in the Turk trick. But I just want to mention this. And then the final thing I just want to say, which again I find it helpful to think about this way, is that maybe the most geometric way to think about the mean curvature flow is in terms of its space-time track. Okay, so the idea is if you're given a say a mean curvature flow, you can form this so-called space-time track, which is just defined as a set of P and T inside of space-time, so Rn plus 1 cross R, such that T is in the interval I and P is in the set sigma T. And the point is you can think of this as, in some sense, a submanifold, possibly with boundary. Of space-time. And this is sort of the most geometric perspective. So again, the idea is here sort of T, you're supposed to get a so for each T, you have sits above it is the sigma T. So here's the initial condition, which is sigma T. Okay, so this is like a one dimension higher submanifold of space-time. And the point is, if you form a vector field EDT, which is partial T, so this vector field is tangent to the space-time track. So the space-time track makes sense for any sort of reasonable smooth family of hypersurfaces. This vector field is tangent to S. This is precisely the same as when you're a mean curvature flow. Okay, so this space-time, this is maybe the most geometric way of thinking of the mean curvature flow, and this is sort of the perspective I'm going to maybe use as much as possible. Though, of course, when you have to do actual calculations, usually you pick some kind of coordinate, so you pick some parameterization. And usually this one, parameterization that satisfies this, everything is the simplest. Okay. Okay, so let me maybe see some examples to illustrate what can and cannot happen. Okay, so the simplest example is just to take a static plane. It doesn't move anywhere, for here is P is a plane. So if you just look at a plane and don't move it, then of course the mean curvature is 0 and it's not moving, so this is satisfying our equation and is the simplest example of of a mean curvature flow. And you can, of course, generalize this more generally. If sigma is a minimal surface, so a different notion of minimal. So in this case, this means that mean curvature identically 0, then of course, similarly, that also are static. So the point about this is the mean curvature flow sort of generalizes the theory of minimal submanifolds. So every minimal submanifold is a mean curvature flow. So you can never sort of do better than the theory of minimal surfaces. And of course, here, sigma is necessarily not closed, because there are no closed minimal surfaces in Euclidean space. Okay, so those are not very interesting. One that's maybe more dynamic is to consider the shrinking spheres. Right, so shrinking spheres, we know for a sphere we can compute very explicitly its mean curvature, and it's just a function of its radius. And if we sort of plug that into this equation, we get an ODE for the radius function, and it's straightforward to solve. And so one can see that in this case, the solutions are, say, sigma t is equal to the square root of minus 2nt. So these are the spheres of radius square root of minus 2nt, and this is defined for t less than 0. Right, so we have this family of spheres defined for negative times that shrink down to nothing as you approach 0. And just again, what does the space-time track look like? It's going to look like a kind of paraboloid that doesn't quite achieve 0. That extends arbitrarily in this direction. Okay? Okay, and then another example, which actually exists eternally, so both forward and backwards in time, is the right. So it's the so-called Grim Reaper. Right, so this is a surface, say sigma t. Okay, so and t is. Okay, so this looks like this guy with sort of asymptotes at. And the point is, it evolves by just translating vertically. Okay, so the mean curvature. Okay, so I'll leave this to you to check. So this is the Grim Reaper. And let me just do one more example, which is what happens when your surface is a graph. Okay, so if a graphical mean curvature flow. Okay, if you're sigma t, so in this case, let's suppose it's entire, just to be the safe side. So suppose you have a function defined on all space and time, say on an interval, I. Right, so we can consider the graph of this function, which is, say, p. Right, so this guy, this family of graphs, this is a mean curvature flow. If you work it out, this is precisely when the function u satisfies a very clearly quasi-linear parabolic equation. Okay, so so this is a so-called graphical mean curvature flow equation. Okay, and we see that this is nonlinear and quasi-linear, but the point is, as going back to what I said before, the only thing that kind of causes problems in getting estimates is when this gradient of u blows up, because that makes this, not be that's sort of your coefficient of ellipticity of this operator degenerates. So as long as you have kind of gradient estimates on U, then you should get good estimates on U just by standard parabolic theory. And so when we're going back to that thing, the first thing I said, which was about how the second fundamental form interacted with being able to express things as a graph, this sort of tells you that, basically, once you control the second fundamental form, you can just appeal to kind of standard parabolic theory to get estimates. So the whole business with understanding the regularity of the flow, in some sense, from the PDE point of view, is built into the understanding the second fundamental form. Okay. But in a very kind of transparent way. It's not hard. There's not a lot of nothing mysterious about it. Okay, so that's some examples. So what are the kind of basic sort of properties of the mean curvature flow, which I maybe take for granted, that I want to mention? Okay, so the first thing I want to mention are what are the natural symmetries of the problem. So the flow has a number of them, which of course is very important in the analysis of it. But the first and probably the least important is there's sort of the spatial rotation. And I'm going to describe these in terms of via the action on the space-time track. Right, so again, we're going to think of space-time, ambient space-time, where we have our space-time track as a hypersurface, and we're going to act on symmetries of ambient space-time will preserve mean curvature flows. So the first one is, of course, spatial rotation. So the idea is here you send a point in space-time to a rotated point in space-time, where here R is some element of the orthogonal group. So this is probably the least interesting, but of course is there. So you can always rotate every hypersurface by some fixed element and get a new mean curvature flow. The second one is the space-time translation. Okay, so this you send a point xt gets sent to x plus x naught, t plus t naught. So in other words, you essentially move the space-time origin to the point x naught, t naught. And that, of course, doesn't change anything in the equation. But this is useful because you can change the way you parameterize time and move things around. And the third, and perhaps most important, is parabolic dilation. So this is what's going to allow us to, say, zoom in or blow down on the different the flows, which is precisely what you want to do in singularity analysis. So here you send a point xt, and you scale space by a factor rho. And as usual with the parabolic problem, if you scale space by a factor rho, you have to scale time by basically the corresponding factor, which is, I guess maybe I should say rho squared here and rho t. Sorry, I have this backwards. Yeah. Okay, so the parabolic dilation is where you scale space and time separately. Right, right? But again, if you're acting on the space-time track, you're sort of stretching everything out, as you would expect. And the point about this is that if you think about it, so these some of these flows are sort of invariant under these symmetries. So for example, the static plane is invariant under, if you think of the space-time track, it's invariant under a purely time translation. The Grim Reaper is invariant under a sort of another translation, but one with moves both space and time. Whereas the shrinking sphere is, of course, invariant under dilation about the origin. So, of course, you would expect these there would be special solutions that are maybe invariant under these symmetries, and we'll come to that soon. So another important property, which, of course, we use without proof, is the sort of short time existence and uniqueness. Okay. So this is, of course, ensures that we have flows starting from most, regular enough initial data. Okay, so what's the precise statement? So for simplicity, we'll just state it for closed guys. So any closed hypersurface sigma naught generates a unique mean curvature flow sigma t in some interval 0 up to a capital T, which is open for some capital T, which is positive and possibly infinite a priori. And this maximal time of existence is sort of characterized by the limit as t increases to capital T of the supremum of the second fundamental form of the sigma t is equal to infinity. Okay. So we know that if we start with any closed sigma naught, then we can construct a mean curvature flow for a short amount of time, and in fact we can continue the flow as long as the second fundamental form remains bounded. A priori for an infinite amount of time, though we'll see shortly that for closed guys it's not, this is actually finite. Of course we can drop the closed assumption. One might be interested in whether we could drop it, and it turns out there are situations where you can do it. The most easy to state is where you just assume a uniform bound on the second fundamental form initially. So bounded curvature has the same result. And again, this result is in a sense standard parabolic theory. The idea is basically, as I said, the curvature controls how you can write it as a graph, and once you can write it as a graph, it's really just a uniformly parabolic problem. So quasi-linear, and you just plug it in and see that it works. Okay, so that's the short time existence and uniqueness. Okay, the other kind of key property that is we're going to use implicitly in a number of places, and has to do with being in codimension 1. So a lot of what I said is not really dependent on codimension 1, but this is the so-called avoidance principle. Okay. So the idea is if we have two mean curvature flows, so let the mean curvature flows, and suppose say one of them at least, so sigma naught prime is closed. Okay, So what the avoidance principle says that is if the flows are initially disjoint, then they remain disjoint as long as they're defined. Okay, and this is a maximum principle result, and it's definitely codimension 1. And has a number of important consequences, which I'll mention. But let me just, if you haven't seen it before, let me give a kind of sketch of a proof. Okay, so let's suppose they intersected at some point. So if this was not true, then let, say, P naught be point be in space-time of first contact. Right, so the idea is because this is where we use that one of them is closed, so since one of them is closed, they have to touch. If they intersect at some point, there had to be a point where they first touch. And so by construction, clearly, just by hypothesis, this has to be a positive time. Okay, so now the point is locally near, say, P naught, we have that, say, sigma T naught is on, one side of sigma T naught prime, right? So the point is we have a picture which is like here's sigma T naught, and here is okay. So we're not saying, we're just looking locally near the point P naught, and of course this is because if this wasn't true and they really went through each other, then if you went a little bit further back in time, they would have still been intersecting, which would contradict the fact that it's the first contact time. Okay, now we can pick normals n sigma of T naught, and so that they're equal, because of course if they touch here, they have to touch tangentially, and also so that right, we have a freedom in which side we choose it, so we're going to so sigma T naught prime lies on the same side of sigma T naught as the choice of normals. Right, so in other words, we have this common value. Okay, so now the idea is because sigma T naught prime is on one side of sigma T naught, you can see that kind of all the principal curvatures of sigma T naught prime have to be sort of more curved than a sigma T naught. So if you figure out what that means, again, you have to think about the signs, but basically it should tell you that minus h of, assuming I did the signs correctly, the scalar mean curvature of sigma prime is greater than or equal to the scalar curvature, the scalar mean curvature of sigma T naught and P naught. Okay. Right, so this is more curved, right, than this guy. Again, think of like a sphere touching the plane, for instance. There are two spheres of different radii. Okay, so the point is, if this was strict, and this is the standard game with the maximum principle, of course, if this is strict, right, then of course the speed of the inner guy at this point is going to be faster in this direction, say, than the other guy. And so if this was strict, then for some small epsilon, we would have a picture kind of like this. Like, just because it's moving faster than the other guy. So that would be a contradiction of the first touching time. Of course, if it's not strict, one has to do, it's a parabolic. This is a kind of standard thing in the maximum principle where you have to deal with the equality by some trick. But this is the geometric idea of what's going on. Alternatively, of course, you can write everything as a graph, and then you really just appeal. You have good control on the gradient, and you look at the difference of the two graphs, and then it's really just the standard parabolic maximum principle. Okay, so that's the proof of this. And it has some significant consequences. So one consequence so the first is that any closed curvature flow has a finite time. Okay, so if you start with a closed initial hypersurface and run the mean curvature flow, then this maximal time of existence t is actually finite. And the idea of the proof is pick a tau sufficiently large so let's say the ball of radius squared of minus 2n tau centered at the origin contains your initial hypersurface. And so then the boundary of this, of course, is evolving by mean curvature flow and shrinks to basically, if you start at time minus tau, this shrinks to 0 at time 0. So this guy has to also become singular before. It always has to be disjoint, so it has to become singular before this guy disappears. Okay, so basically a shrinking sphere. Okay. Another very important consequence, which again you've probably certainly seen, is that there exists, at least when the ambient dimension is 3 or more, there exists, say, closed hypersurfaces that become singular. Right, so the sphere is interesting because it becomes singular precisely where it disappears. But you might wonder if that always happens, but this example shows that it doesn't. So there's examples that become singular before disappearing. Right, so this is this classic example of a neck pinch. This is the so-called neck pinch. Right, and the heuristic picture is you have two very large spheres joined by a small, thin neck. And this is where we need to be in dimension 3. ambient dimension 3 or higher. So the idea is the mean curvature here in these spheres is significantly smaller than the mean curvature here. So you would expect this neck to collapse before the spheres do. But that's, of course, not rigorous. You can make this rigorous, though, by putting two spheres inside of the balls, which sort of act and prevent the flow from disappearing, because they can't disappear before the spheres do. And then, I mean, you have to find an example of this, but we'll discuss soon an example that will work, something that will force this neck to pinch quickly. So there exist such examples. And so if you evolve this, it becomes singular with a kind of singularity that looks kind of like this in finite time. Okay, so that's the the sort of basic setup. And one final consequence, which I don't know if I'm going to get to in time. So again, but maybe I'll just say it in words, right? I mean, one of the things we observe is now, because singularities form in the mean curvature for closed initial sets, there's certainly interest in analyzing the singularities. That's what I'm going to focus on the next few lectures. But there's also a question of, can you continue the flow past the singularity? So that would require a notion of a weak mean curvature flow. And there's sort of two candidates, at least two candidate approaches to that. So one is based off this first variation formula and the kind of variational definition, and trying to make sense of the flow as a flow of, say, a surface measure. Another one is to use this avoidance principle and kind of form a kind of viscosity type solution, where you think of it as set theoretically. So they are both important flows, and if I have time, maybe I'll mention them. But the idea is this maximum principle gives you a way of defining a certain notion of viscosity solution in at least in codimension 1 that's very well behaved, and basically, exists past the first singularity time with reasonable properties. Okay, so maybe I'll stop here now and then